In this video lecture, we're going to start talking about thermodynamics and talking about how energy relates to chemical equations. Today's first video lecture, we'll talk a lot about calorimetry, then we'll talk about Hess's law, and then we'll deal with some of the spontaneity and Gibbs free energy and how that relates to why some reactions happen easily and others don't. As we think about what goes on in a chemical reaction, we're going to talk about the relationship between chemical reactions and heat, what causes chemical reactions to occur in the first place, and a lot of times we're dealing with energy. We're going to talk about things called enthalpy, which is kind of like energy, entropy, which is disorder, and then we'll also talk about the idea of free energy. When we deal with free energy, we'll talk about how some things want to happen spontaneously and other things do not. First things we want to get straight are the difference between systems and surroundings. A system is the species that exists in a chemical equation. These are the elements and the compounds that are actually in the chemical reaction. The surroundings may be like the glass beaker, maybe the air around the beaker, maybe the rest of the universe that's around the air. If you're dealing with something in an aqueous solution, it may be the water that heats up. Those are the surroundings. There's always a transfer of some sort of energy happening between systems and surroundings all the time. Two processes that you're probably familiar with already is the idea of endo and exothermic. The prefix endo means that it goes inside. That means that there's going to be heat that is flowing into the system from the surroundings. Heat always moves from warmer to colder. It never happens the other way around. It always flows in and out of the system. Temperature doesn't flow, heat does. A system of ice has less energy than the same system will have when it turns to water. The temperature is the average kinetic energy of the system during one of these phase changes. So you would not see it change during one of these. It would flatline if you've seen that on a phase diagram before. As heat is added, the internal energy of the system increases with no increase in the temperature. And what's happening is during that phase change, that energy is being put in there to sever the bonds and break the solid apart into a liquid. When we have an endothermic reaction, the products have more potential energy tied up in their bonds than the reactants did. The extra energy that's absorbed ends up locked into the bonds of the products. Now, in an endothermic reaction, it's going to pull energy into the aqueous solution, and pull the heat out of the water and the glass beaker. So if you put your hand around a beaker that was experiencing a endothermic reaction, it's going to feel really cold to your hand. Now, that's not because the temperature is flowing, it's the heat that's flowing. It's not cold that flows, it's the absence of heat that makes it feel cold to the touch. So in an endothermic reaction, there is energy being taken out from the surroundings and put into the reaction. That's endothermic. The products have more energy than the reactants do. Exothermic processes are the opposite of that. This is an example of methane being burned. If it's burned, it's going to give off heat. You've experienced this when you've burnt with a fire before. So when you have CH4 and O2, it's got more energy than the same system will have when it has all become CO2 and water. What does that mean? That the bonds in the products have less energy than the bonds in the reactants, meaning that CO2 and water are more stable because they don't have a ton of bond energy. The difference in this energy, the reason it shoots out, that's in the form of heat. Some of this energy changes in the form of pressure and volume. As that happens, the heat gets released and it causes the gas to expand. The gas expands is another form of energy that can do work. Work is a force times distance that you do on an object. We in chemistry only tend to focus ourselves at the heat that's lost or gained, and that accounts for most of the energy that happens. So in an exothermic reaction, the energy from the product, the reactants, is released out to the surroundings. So you would feel that energy in the form of being hot to the touch, because the energy goes from the reactants to the products. So the heat is flowing outwardly because we're seeing products with less overall energy. So what does this term enthalpy mean? Enthalpy with this delta H sign, enthalpy is H. You can think about it as heat being released or absorbed. This is a pretty important equation here. Delta H is the net change in heat. H of the products is the heat of the products, and H, the reactants, is the heat contained within the reactants. A couple things to realize about this. If you ended up having an endothermic reaction, you would have a positive delta H. That means your products ended up with more energy than the reactants within their bonds. If you had an exothermic reaction, delta H is going to be negative. The potential energy is locked up in those chemical bonds. Let's talk about how this works with an example. If you are going to burn hydrogen fuel for your car, 2 moles of hydrogen plus 1 mole of oxygen to make 2 moles of water, that releases negative 572 kilojoules of energy. That is exothermic in this case. That means you're going to release that much energy per 2 moles of hydrogen. Notice what happens though when we flip the reaction in reverse. When we have 2 moles of water to get 2 moles of hydrogen plus a mole of oxygen, that requires 572 kilojoules of energy. What does that mean? Well, if we think about the 2 moles of hydrogen, the 1 mole of oxygen, they've got more potential energy tied up in their bonds than the 2 moles of water. So notice that the sign is different. It just tells you where that energy is stored up in. If you go back to this enthalpy of reaction, when you see that negative sign, that means the reactants had more of that energy stored up in them, if it's exothermic. If it's endothermic, the products have more energy stored up. Take a look at how that relates here. More energy tied up. In this case, it's products minus reactants. There's more in the reactant side. Take a look at that negative sign. That means the reactants had more energy here. But to reverse it, it would require 572 kilojoules of energy. Notice delta H is the same number, but opposite signs. So it's all about where the chemical bonds are at and how much energy is stored up in those chemical bonds. Here's a diagram of what happens. If hydrogen and oxygen are burned, it releases negative 572 kilojoules of energy to form 2 moles of water. That's great. Opposite side of this, if we want to go water back into hydrogen and oxygen, 572 kilojoules of energy have to be brought in. So notice that the magnitudes are the same, but there is an opposite sign. If we double the number of moles of each molecule, the amount of energy released would be doubled. Burning twice as much gas in your furnace would release twice as much heat. When you're going one way and have to put 572 kilojoules of energy in, when you go the other way, it releases 572 kilojoules of energy. So the process, the numbers are the same, but the signs flip. Heat versus temperature, we measure heat in the form of joules, capital J, kilograms times meters over second squared. We think about that in physics. Joules, we're talking about measuring heat in this case. Temperature is the average kinetic energy of the system, and we measure that in degrees Kelvin. Remember, it's not really degrees Kelvin, it's just Kelvin itself, because that's the absolute value scale. You can't ever get below 0 Kelvin. That's a measure of the average kinetic energy of that system. So when we think about how that applies, we need to measure heat a couple of different ways. We're going to look at using a calorimeter here, and we're going to be doing a lab here pretty soon on doing calorimetry. Hess's law, which is kind of the stoichiometry stuff that we'll deal with later, and then enthalpies of bond formation and average bond enthalpies. Calorimetry, and we'll stop after we talk about calorimetry a little bit. This is going to really measure heat flow, and a calorimeter is the way that we measure that heat flow. We can't measure the heat flow directly within calorimetry, but we can look at how it flows and how it changes temperature. So we use an equation in calorimetry called the specific heat equation. Delta Q is the heat lost or gained by the water. M is the mass of the water. C is the specific heat, which is a unique thing for water, is specific temperature. And delta T is TF minus TI. What this means is the delta Q is the amount of heat required to raise the temperature of 1 gram of substance by 1 Kelvin. Water has a huge value for this, 4.184 joules over grams times Kelvin. It takes a lot of heat to increase the temperature of water. It's not a great conductor. It has a high specific heat capacity. It means that it doesn't readily transfer the heat very well. Look at that value compared to gold, or excuse me, for iron in this case, 0.84. That means it only takes 0.84 joules to raise 1 gram of iron 1 Kelvin. That's not very much. Whereas if you dealt with water, it would take 4.184 joules to raise 1 gram of water 1 Kelvin. So things that are really good conductors have really small specific heat capacity values. The Q in this case is really just talking about the heat being lost or gained. And it involves numerical quantities of these reactants and how they work together. This is a picture of the calorimeter that we're going to use in the lab this week. We're going to use a coffee cup with a lid with 2 holes in it. We're going to do a chemical reaction inside of it, and we're going to take the base initial temperature of the water, see what it is before the reaction happens. That will be our TI. Then as we mix that together, we're going to see how that temperature goes up or down to look at the energy, the heat being absorbed or released into the water by the reactants or products in the chemical equation. So when we think about what goes on, we're going to know the specific heat capacity of water. That's a constant, 4.184 joules per gram Kelvin. We're going to know the mass of the water in the calorimeter. We're going to know the initial temperature of the water in the calorimeter. And we're going to know the final temperature once it stops going up or down. So we can use that to calculate the heat lost or gained pretty easily with our Q equals MC delta T. Now, thinking about what happens, we're going to know every value in that by setting up our calorimetry. So this Q is going to tell us if it's a positive value, we're going to see that being released. If it's being absorbed, if it's negative, we're going to see it being released with the Q values. The heat lost or gain of the water is equal but opposite to signs of the heat lost. So if you calculated Q to be positive 568 joules, the water gained heat, that means the reaction was exothermic. Positive, that means it got hotter. So that means it's exothermic. So the heat of the water is equal to the heat lost by the reaction. Here's an example of a calorimetry problem. 0.075 moles of HCl are mixed with 0.075 moles of sodium hydroxide. They're added to 150 milliliters of water in a coffee cup calorimeter. The temperature of the solution increases from 23 to 29.9. Calculate the enthalpy change for the formation of 1 mole of water in this reaction. Assume that no heat is lost or gained in the surroundings. So we've got our base reaction. There's our net ionic equation. We've got acids plus bases to give water. That's the net, just like we have been doing. Step 1 is find the Q. Q is equal to MC delta T. Now, a couple things to realize about this. When we are dealing with QMC delta T, we have 150 milliliters of water. Well, the density of water is 1 gram per 1 milliliter. So if I have 150 milliliters of water, that's the same as 150 grams. Since we're dealing with water in the calorimeter, we know it's 4.184 joules per gram Kelvin. And then we have the delta T. T final, which is 29.9, minus T initial, 23.0. Plugging that all in, we get a Q value of the water of positive 4,330. Now, this thing got hotter. Heat was flowing from the reactants to the water. That's why the temperature went up. So that makes sense why the Q value is positive. It's exothermic. But you told me, Mr. Ibbotson, earlier that delta H, if it's a negative, is exothermic. Remember what we said. Once you find this reaction, the water absorbed by the heat gained by the water is equal to the heat lost in the reaction. Same number, but opposite sign if you want to find enthalpy. That's H. The reaction is exothermic. If the Q was positive, the reaction released energy out. So the water got hot. So the Q of the reaction, negative 4,330, opposite in sign. The water was positive, but the reaction is negative 4,330. Same number, opposite in sign. So we look at the water's effect, and we look at what actually happened in the reaction. From that, we can find the heat of the reaction, the enthalpy of the reaction. That equation is found by taking the Q of the reaction divided by the moles of water to get 5.8 times 10 to the fourth. Now, it's a negative sign. So the heat of this reaction was negative 58 kilojoules. We took the energy of the reaction divided by the moles of water that we formed, that we dealt with, negative 58 kilojoules. Q of the reaction is the heat lost or gained in the experiment that took place in the calorimeter. The delta H, or enthalpy of the reaction, is the heat lost or gained in the balanced chemical equation. The Q is dealing with the water within the coffee cup. This is dealing with the stoichiometry. Same number, but opposite in sign of the Q reaction. We'll stop there for today on the video lecture. We'll deal some more with calorimetry this week. Thanks.